Good afternoon and welcome to this talk given by Dr. Ntsikelelo Charles. Dr. Charles is a graduate of Rhodes University. So for me, it's a pleasure to welcome him back home. I mean, how do you welcome someone back to their own home? Ntsikelelo Charles graduated with a PhD in 2024. And I think if I remember correctly, he studied something to do with data analysis from the HERA telescope, something to do with the era of, with the epoch of reionization, which is something I think the astronomers know most about. Before that, he received his master's degree in 2021, having completed his honors degree in 2019. So, you know, I still remember the facts. Okay. Today, he's going to talk to us not about the era of, not about the epoch of reionization, but about the era of precision cosmology. So, Charles, please. Thank you very much.
I can just add a few words as ex-supervisor. So, Ntsikelelo almost made two mistakes. Well, not really mistakes. He corrected them very quickly. For some reason, he decided to study mathematics. Well, I'm joking. I also studied mathematics. But to ours and his good fortune, he somehow found his way to us for his master's and for his PhD. And a lot of that supervision, I think, was during COVID. I remember in lockdown, we used to have these long meetings and they always ran over time because it was just so much fun to work with him. Really, some of our most pleasurable supervision meetings were with Ntsikelelo. Then he made a second mistake. He went northwest for some reason. Fortunately, we were able to correct that and to get him to come work at Cereo. And as you know, Rat works very closely with Cereo. So in his capacity at Cereo, he is practically a Rhodian again. Well, he is an honorary Rhodes associate. So we are, you know, very delighted to host him here and have him speak to us.
Let me just get my pointer. All right. Wow. Thank you everyone for attending. It's great pleasure to have to give this talk to you today. It might be very boring for those who already know a lot about radio astronomy. That's not the point of this talk. The point is for those who don't really know much about cosmology or radio astronomy, okay? But somewhat at the end, I'll lose half the audience. Again, what's a cosmology talk without losing half the audience by the end, all right? So by the end, please don't be frightened if you don't understand something. It took me, 7 years to understand the stuff as well. All right, so I'll start briefly with cosmology. Before we discuss the precision aspect of cosmology, let's start with cosmology first. Well, okay. All right, so for that, we start right over here. Well, I thought this would work. Nope. All right, I guess it doesn't. Then I'll just use mine. All right, so cosmology. Well, I'm going to start quite early, very early, back when we only had our eyesight. No technology whatsoever. We look up in the night sky. Maybe we spend most of the time at night sleeping. So this is what we looked at. We had the sun. Sometimes we could see the moon as well. But eventually, when we could look out in the night sky, stay awake as human beings, probably saw some of this stuff. And people started trying to come up, okay, what is this place that we live in, right? And that's the aspect of cosmology. So it's not crazy that people came up with this image because it makes sense. Everything around us, okay, is tiny, small little dots in the sky, and the Earth relatively is big. And so that's how the picture was back then. And then you have the sun, of course. I doubt you had Andromeda that big. Okay, but we'll discuss that a little bit later. But this is the picture that we had back in the days. Well, that somehow changed when scientists developed some technology, for instance. This is a picture that I found online of Galileo, okay, looking out in the night sky using a telescope. Okay, that really changed how we view our place in the universe. What did he find? He found these nice objects that seem to move relative to the background stuff. Okay, and we call them the planets. All right, and this was great. Okay, and they figured out that, well, they move, then the whole thing changed our model. It was no longer called the flat Earth theory, but it was the heliocentric model, where we now had a planetary system. So we found our place in the universe where we had the gigantic big sun right there at the center, and we found ourselves as just one of the planets amongst in that solar system. This was great, but remember at the time, no one had the technology to move out and have a view of the solar system from space. So we relied upon models, okay? And that's the theme of this talk, cosmology, but now we talk about precision, and precision leads to definite models. Okay, so going back to this, we got a solar system, and we did some good stuff with this, okay? Technology again made us travel to the moon, for instance. Now we could see the Earth from another object in, well, a different perspective of the Earth. And finally, we could see the Earth is indeed not flat or big, okay? I hope that is settled, but you never know these days, all right? And we did better, okay? It's not just we visited the moon, but we visited other planets as well. For instance, well, that's a dwarf planet now, that's Pluto, right? And there's also planet Mars there. And we had a couple of instruments that went there. And that's the, I like that one. It's really fantastic. The last picture there, which is a rover on the surface of Mars. For me, it's a privilege to live in such an era where you can actually see the surface of another planet. Of course, no human beings went there, but it's great to actually see the surface of another planet. Now, this is all great, photographic evidence, everything is reliable, okay? But that doesn't end there. Remember, I mentioned what else is out there? There are these stationary bits, okay? They're not moving as the Earth rotates or anything like that. As time progresses, they're more or less stationary. What are those? These tiny objects. Well, it turns out those are just the stars, and they are just different suns, if I can call it, and they're all varying in different sizes. For instance, we have Betelgeuse there that is big. From this image, you can't even see our sun. It's that tiny dot that's there. So the universe itself is complex. You know, it's not that simple. Those tiny dots in the sky are actually huge things like suns, for example. Okay, and we see that our sun is just a tiny, well, tiny sun amongst bigger ones. And these stars do incredible things. For instance, they grow and eventually explode. Now, I won't get into the physics of why they explode and why all of that. That is something that people study for years as well. So I won't touch on that. But they explode, they undergo supernova events. Well, how do we see this? Well, it turns out there are a lot of stars out there at different stages. So what you see when you look out in the night sky is this. These are supernova remnants, okay, where the star has exploded. So certainly, there's a lot there that's happening. Stars can explode, and we see them in different stages of their life. Well, what else is out there? Galaxies as well. For instance, here, this is an image of the Andromeda Galaxy, okay? And we made slightly better images of this. This I took from the James Webb Telescope. And it's an incredible image showing now what we call a galaxy. Now, what is a galaxy in a sense? We had the stars, we had the galaxies. The galaxy is now a collection of those stars and all those planets, and they form a galaxy. which kind of hints, are we also in somewhat in a galaxy as well? Yeah. Every time we look out in the night sky, this is what we see. That is the plane of our galaxy. Now, this is great. In the optical regime, okay, if you look at it with your own eyes, there's a lot of dust covering that. Okay, you can't learn much about the inner workings of our own galaxy with the light being blocked from there. But what else can you do? Look at the very same patch of sky, but with radio waves. Now the dust suddenly disappears. You can pierce through and study the inner dynamics of our solar system. Sorry, our galaxy, okay? So that's the advent of radio waves. So these are really nice. I haven't gotten to cosmology yet, but we're going up by scale. Now we're at the scale of galaxies. So now we are probing galaxies, their existence, all right? And here we go. Now remember, we've never actually taken a picture of our Milky Way galaxy. What we rely on are models. We can map out the structure, right? The spiral arms of our galaxies using some, there are mazes. These are mazes, which are radio emissions, and you can use those. They're usually in highly dense region, and you can use them to map out the spiral arms of the galaxy. But the point is, these are still models. Okay, but at least with this model, you have examples of galaxies, okay, that you can at least fine tune, at least understand. The terrible nature of cosmology is that we only have one universe. There's pretty much that, and that's it. So that's why we have a lot of models. We need data to constrain those so that we can finally know the true nature of our universe. Right. Now, of course, there are globular clusters, a collection of stars, collection of galaxy clusters as well. And galaxies, again, do interesting kind of stuff. For instance, here, they can collide. And you can see different stages of that collision. So this is a very nice simulation where someone is simulating galaxies approaching each other about to collide. And what you can see is they can actually map now certain galaxies at different stages, in our own universe. And which is a very nice thing to have, because now you can actually map your models to an actual data. For instance, here, those galaxies are at different stages. Now, amongst us here, there are people dedicate their lives in studying galaxy measures. Okay, I'm not an expert in that. I'm not focusing on this, but on the larger scale of things. So I don't have the privilege of looking at examples or anything like that. Okay, so let me just get through this. And of course, galaxies have interesting stuff. The reason why I put this here is actually relevant to my talk, but it was a privilege that I could understand how that image of the very first black hole was produced. 2 radio waves. It turns out amongst the stars, for those who don't know, while listening in the audience, for every galaxy, you have this gigantic, highly dense stuff we call a black hole. It took us 4 years or 6 years for me to understand. So I'm not gonna try and explain that to you now. Just accept it as it is, that, there's amongst the stars in the galaxy, there's also at the center a supermassive black hole. How this supermassive black hole form, that's a question that we haven't answered even. But anyway, let's continue. And again, you can probe these galaxies and how they evolve to different ways of looking at it. You combine optical data with radio data, then you get the mechanism of the interesting bits that happen there, okay? And again, this is not what we do. We focus on the larger scale of things, okay? And again, all those images are produced by a nice telescope. That's the Meerkat telescope. And over there is the EHT that produced the famous image of a black hole. Now, it turned out at some point that they pointed the Hubble telescope at a very empty region of space, okay? And what they found is, well, as I'm talking, what they found is that if you leave that or observe that area, that patch of area for long enough, long exposure, what you find a relatively empty area, this is what you find. More galaxies. Meaning that indeed, the galaxies that we're seeing with our eyes, telescopes, and all that are not the complete picture. There's actually more stuff that's there. In fact, the James Webb Telescope is kind of embarrassing cosmologists at the moment because it's finding galaxies at really high redshift, which is not great for us because it doesn't fit well with our models for now. But I'm not going to discuss that here. But the point is, the question of our universe is not that simple, okay? And so, for instance, here you have more galaxies that you may not be able to see with your own eyes. Well, what happens next? We form cosmological models because now we don't have an understanding of what's beyond. Okay, we can only see so far, right, with our optical radio telescopes. But an interesting observation was made somewhere in the I might be wrong about this, 1920s or so. That might be too early, okay, by Hubble. He noticed something that galaxies were seemingly moving away from each other, okay? And why they're moving away from each other, we don't know. What did we do? We call it dark energy. We just said, well, there's this stuff that fills space and it drives galaxies away from each other. Is there a correspondence with particle physics? Not yet, we don't know, but hopefully one day we'll find something there. But except for this fact now, that there is this mysterious stuff that's in space that's pulling all the galaxies away from each other. Galaxies that are not gravitationally bound to each other, okay? Another aspect is dark matter, okay? All these things are dark because, not because they are intrinsically dark. It's just the sky is dark and they don't interact with light at all. So they're transparent. In fact, the convenient phrase to use is transparent material. Okay. So how did dark matter come to incorporated in cosmological model? Two observations. This is what we see. This is a rotational curve. Based on the amount of mass that's in that galaxy, the rotational curve should follow that dotted line. But what we find from experiments, data that is the rotation curve, which kind of hints that there's actually more mass that's there that's not actually giving out light. And that's how matter came into the picture, okay? Now, how do we know all of these things are there? Let's move on. Now I need to introduce a little bit of cosmology without taking too much of time. So we have dark matter, we have dark energy, and we have our normal matter, okay? There's a framework in physics which was developed by Einstein, it's general relativity, it's called. And over here, I'm showing an example for instance, in order to calculate the dynamics of this system where you have the sun, the earth and the moon, you use what we call general relativity, and there's a metric associated with that and all that kind of stuff. But for those who know, this metric is, we assume that the universe is homogeneous, okay? And it's also spherically symmetrical, okay? And that's a very simplistic metric that we use to model the universe. Again, in this model, we're trying to capture all the dynamics of the system. But our system is mostly composed of dark matter, dark energy, and normal matter. Okay, we take these equations, nice equations, takes years to understand them. For now, I don't expect you to do that, but all I need you to take from this is the inputs to these equations are the three components: dark matter, dark energy, and normal matter. And then there's also this one aspect, which is called the curvature of space-time. Yeah, I'm not gonna talk about that for now, but imagine that the bulge caused by those objects that will be the curvature of space-time. And indeed, the universe is indeed homogeneous on large scales. This is just a picture that I took from that. Okay, so, and the universe can either be curved in certain ways, can be closed, flat, or hyperbole, okay? These are all nice terms that most people probably will understand here. But we want to find out, all these play interplay and give us our universe. Okay, so we have our universe, it's expanding, and it's made up of normal matter and dark matter. And remember, the universe expands, so its density weakens a little bit because now it's expanding. Okay. Or the matter density, that is. Okay, and then we also have radiation in our universe as well. Okay, and radiation is given by all the relativistic particles. Okay, particles that travel at the speed of light, very massless. And then we have our well, how should I call it? Non-trivial, exotic material that we call dark energy. Okay, which again exerts this negative pressure that pulls everything apart. Well, you combine all of those, okay, into a nice equation, okay, and what you see, it turns out that if you look further enough into space, you see something that's called the cosmic microwave background. Now, this is looking beyond those high redshift galaxies that I was showing. This is like beyond. This kind of emission is in the microwave regime, okay? It's solely high redshifted. It's almost the afterglow of the very first few seconds after the Big Bang. It's called the hot Big Bang model. Now, this light here only came to us 3,000 years later, okay? So matter, radiation, and all that kind of stuff had time to, interact with each other. Okay, and so what you can then use is you can put in your model, put in all your ingredients. Okay, start off with radiation because purely at this 1 second after the Big Bang, it's so hot, there's no matter that you can form. So what you do is you start off with that, but again, you still have well, at the time it's so hot, nothing exists. That's matter. Eventually, dark matter decouples from the radiation and all that kind of stuff that happens. There's a lot of details in this I'm leaving out, but you run the mathematics, put in all the ingredients, okay, and you try to produce this map. Now, that map, this depends precisely on the amount of dark matter that you put in, the amount of dark energy that you put in, and the amount of curvature that you account, and it produces this nice, what we call a power spectrum. Okay, it basically tells you, well, let me not go there. It produces something nice, which is a power spectrum. For now, this is something that we observe as astronomers. The moment you can constrain this, you can then constrain how much of dark matter, how much of dark energy makes up that, creates that map at the end of the day. And that's what we do. Okay, it's very complicated, not for other people. For other people, indeed it is. You do a Bayesian inference on that, okay? And you get what we call a posterior distribution, which is basically a sense of, it tells you basically what is the range of parameters. For instance, with dark energy, it tells you the range of the values that are allowed for dark energy. So it's a framework that allows you to constrain, okay, your matter, the curvature, as well as the dark energy component. Okay, you can use this using the CMB data as well as BOA, but it depends on the couple of things that you can still do. So it's not conventional as well, but you can still use CMB. Now, all this is great. So now we have some precise measurement of the amount of mass. The universe is flat again, and we know exactly how much dark energy there is. What is the problem then? Well, if you ever want to embarrass a cosmologist, talk about this problem. It's called the Hubble tension, okay? And what it basically means is, remember the picture that I showed of expanding galaxies, all right? They're all expanding at a certain rate. So if you start off, for instance, if you look at the blue line, okay? If you use that simple cosmological model that we call, that contains those two components, you get an expansion rate that's around 67 kilometers per second per parsec. What is? You have been signed up because you're currently signed. Okay. I'll just say okay to that. All right. If you run that model, that's the value that you get. But you can also measure this expansion rate using actual data. This is a little bit complicated. Use the supernova data. So what you do is for each galaxy, when stars explode, their light is very bright, very, very bright. Sometimes they can outshine the galaxy. So even if a galaxy is further away from you, you can actually detect supernova kind of light. And so what you can do is you can measure the distance to those galaxies and measure how the redshift. So in other words, you can then figure out how much the universe is expanding independently though, independently from the CMB. And I just gotten to a point over the years, in 2000, no problem, we can deal with that. Over the years, it progressed until those two measurements exclude each other, okay? Two things here. What it means is either we need to really check our calibration of supernovae data. People working in that field will say, no, we're certain about this. Our cosmological model is not right. We need to do some couple of things there to modify that. Those guys said, no, we definitely sure about what we're doing. And so you have this nice tension here. Now, what can we do about this? Well, here comes me, my science, okay? Remember I told you Big Bang, okay, right over here. Supernova data, right over here. Missing gap, there. And that's called the period when the first galaxy is formed and then began to ionize the intergalactic medium. There's no data that's there. But imagine if we could perform the same experiment, okay? But run it through this entire unexplored region. Then we could figure out where this tension is coming from. Is it the supernova data that's wrong? Is it the cosmological model that's wrong? Okay, and that's what we are trying to do. And again, we can get a sense of this because there's this time light thing that goes on. So this is my work. It's another fancy experiment for antenna like Meerkat. We're pretty low on budget. That's because we had to make 350 antennas. Meerkat has how many? 64 on more for now. But we had to have 350. Why do we need 350? Because we are looking in deep in space when the first galaxies were forming. So we need really high sensitivity to probe that area. And that's called the hydrogen epoch of reionization array. And how can we trace the matter during this time? For physicists who know this, it turns out there's plenty of hydrogen there, and hydrogen has this sort of traceable emission that it emits called the 21 centimeter line. So as long as you can trace this line, you can then trace the matter distribution, calculate the power spectrum, constrain your cosmological parameters. Very simple. The complex bit, though, as always, is that, yeah, hydrogen, that emission is a bit complicated because it's driven by various mechanisms that you need to understand first before you infer the matter power spectrum. One of which it's coupled to the CMB radiation. Remember, in the background, you have radiation coming from the CMB. You also have gas collision amongst the hydrogen atoms. Those influence the spin temperature, according to the second equation. And the other stuff here that I'll not mention. But for simplicity's sake, you can map out the density over there and you calculate this parameter here. So this is the observable that we're trying to get at this era. It can feed us this, which links directly to the matter distribution. But again, the couple of things that brightness temperature depends on. Okay. And hence there are several cosmological models. This is what we're aiming for. This is a simulation, okay, where this started off. For instance, here, the first stars form. What they do, we think, at least for now, we know that they start heating up the intergalactic medium. They start heating up the hydrogen, okay, in between the galaxies. Start heating it up, and eventually, they want to ionize that intergalactic medium, and everything is ionized at the end. Now, our data is not good enough to constrain this. Hence, we can map directly to the matter power spectrum so that we can constrain our cosmological parameters. Hence, we have entered a new era where now data is crucially important to constrain cosmological parameters. You can see spin temperature is highly complex. Well, not highly complex, but it depends on a number of things, not just the matter distribution. Okay. A lot of people have seen this plot, so I'll not talk about it for now. But yes, spin temperature is complicated. There's a lot of stuff that happens to it. But this is what we're trying to measure, basically, the power spectrum. And for different models, this will give a different shape over redshift, which is the distance from us all the way to when the EOR period. That's what we're trying to get to. Now, unfortunately, whenever you have these measurements from the EOR, you can't use them independently. You have to combine them with several independent measurements. So some independents constrain certain parameters, some constrain other parameters. For instance, when we compute our likelihood, we combine it with some data from, I think, the optical depth, Thomson scattering, there's a CMB stuff as well. So we don't just purely use what is this? Data from the EOR. Okay. And the point of this talk is to actually show where have we gone. Now, this is a very complicated plot, but I need you to focus on two things. Okay. There's blue, is that purple and orange. There's with HERA and without HERA. Okay. These are cosmological parameters which people here cannot see. So I'll move that there. These are some cosmological parameters. All right. The various types. But what you can see is even with or without HERA, most of them are constrained nicely. But with HERA data, what we're able to constrain is this parameter. Okay. You can see in the orange bit, there's no constraints at all. All values are pretty much allowed. But as soon as data from HERA came in, we were able to do a little bit of constraining of these cosmological parameters, okay? And indeed, that's what we did. For instance, this is another complicated stuff. Again, this is what we constrain, all right? That's the parameter that we constrain. You can see without HERA, no constraint. With HERA, there's constraint. What does this all mean? Well, we knew that the so-called population 2 stars seeded our stars in our universe. And so this data maps out very well because what it really says is that the stars, okay, we map out the X-ray heating mechanism and all that stuff, but the stars that heated the intergalactic medium were the so-called population 2 stars, which lack in metallicity. It's a quite technical term, but they are basically, how should I describe this? They are the next generation of stars. So populations 2 stars give birth to our stars that we now know and love, I hope. Okay, so that's what we did with HERA data. Now, what's the remaining issues? Well, 21 centimeters right over there. It's a very weak signal. Again, the stuff that's in between, okay? In this case, extragalactic foregrounds, okay, remember those galaxies, they also produce radio emission. You also have our own galaxy also producing some sort of emission. And so you need a way to account for this so that you can extract the EOR signal. This turns out it's not an easy job. Clever ways to do this, which I'll not discuss for now, but those are some of the problems that we have. Okay, and then the next thing is, whenever you're taking data, it's not as simple as people planned it. Instruments never behave like you wanted them to behave. That's the reality of taking data at the end of the day. And so my work was to try and see what we can do with this. For example, this is what we allow the antenna to behave like. That's the sensitivity pattern of an antenna. This is what it behaves like on first order when we model it. Okay? What it means that when I say on first order, it means we're not completely modeling the effects of it. Only up to first order. And you can see the behavior is very abrupt, changes quite a lot. Now you can imagine the worst case scenario when you have to model the entire thing. So this is something that we can't account for. Well, what I did is, then what does it do? It messes our power spectrum measurements. So the black line here is the power spectrum, the expected noise level of the power spectrum. But you can see somewhere along the low K modes, okay, right over here, the power spectrum measurements do not follow the noise, and that's because you've got systematics in your data, and you don't want that. Because if you try to fit anything with systematics, all you get out is not good science at the end of the day. So you need to deal with that. And how did I do that? Well, I did some clever ways with the help of Landman, Oleg, and Gianni. Gianni is not here, unfortunately. But this is not an independent work. This is not just my work. But we did a lot of stuff. If you focus on the very right plot here, okay, the blue line, that's what we wanted to suppress. And indeed, we did that some clever ways. If you look at the green line, the blue line there, as well as the yellow line, that was indeed great. So that's when you don't have a complete, accurate depiction of your foregrounds. In other words, of those intermediate radiating physical objects in between you and the EOR. And then here, it's mutual coupling. And we managed to suppress that. And you can see it goes all the way, but not sufficiently as that one. But that's okay, because we expect the EOR to be somewhere right over here. So we managed to suppress this. Then here you say, well, it looks like you've solved the problem. Yeah, in simulations. The actual data is very complicated. That's the next frontier of my work, is to now use the very same thing to try and get rid of the systematics, but it's proving to be a pain for now, but you can always push through and get that. Now, sadly, yes, I've been paid by NASA. Actually, the Earth is flat, and none of the stuff here matters. But the last thing I want to say is, when I first approached Prof. Chitamba for this talk, I didn't anticipate that it'll be a big event. I saw the comments on the social media, and I was really encouraged by that. And I really just want to thank the people, the community of Makanda. It was great having you guys here, and those guys online, my friends. It was great to have your support for this. Thank you. Oh, yeah. Yes.
Any questions for Charles?
Well, maybe Charles to give a two-third question. Ask him one more question.
Yeah.
Which part are you talking about that is the precision part?
Okay, so the precision part is the corner plots. They're loosely constrained, most of it. But what we're trying to get to, if we manage to constrain those parameters as tightly as, for instance, in this one, then we get a better sense of which models are viable. Because at the moment, most of them are still there. We've excluded some with the current data, but we need more data. The 21 centimeter signal, we haven't detected it yet. But we have clever ways to constrain parameters still. So precision means narrow parts here. And all of these parameters, it's wide, loosely constrained. And that means we don't know the ingredients that make out our universe. And there's no universe for us to look at, so we can sample some stuff and be okay with this. We have to just try and get more data. Hope that answers the question. Okay. Yes. Okay, so remember when I showed the picture of the galaxy, for an example? Let me just go back there. And I alluded that actually no one has ever taken the picture of our Milky Way galaxy. That's a model, okay? There are various variable models that can still produce this. In other words, they're degenerate, okay? The data isn't good enough to constrain so that you can have one unique model that perfectly produces your galaxy. I mean, cosmologically speaking, we're not planning on getting there. But what we're trying to do is exclude a large portion of the models. Because right now, every now and then you see a different cosmological model that's very much valuable, and you need the data to push those models out so that we can refine, our models and get to this unique set of models that perfectly describe our universe. So that's what I mean by precision. We need that narrowing or constraining of cosmological parameters, which then exclude a large portion of not so viable cosmological models. Some of them you think someone just wrote something and then it worked, it fitted very well, but it's not physically motivated or anything. But you can't exclude it because it fits the data nicely. But if you constrain, if you have nice, precise data, then you can exclude such models. Yeah. Kate. Yeah, either. Yes. How do we know if so they were worried about the data currently have? Oh, yeah. Okay, now we're using the hydrogen group. Okay, so in that sense, precision is not the problem because you can see that they mutually exclude each other. The problem is that it's inherently in the physics. It's either there's a systematic error in how we calibrate our supernova data, and those guys would say no, or the lambda CMB model is not a good model that we should use. So in that sense, that's where the big problem is. But now, if you can now probe an error that's independent of those two, because remember, the CMB is highly redshifted, and the supernova data comes locally from the local kind of data, low redshift. So you have this in-between space. And that's where this sort of independent observation would try and bring about, okay, who's wrong? I hope that's all right. Let me just get Kate and then I'll give it to you. Kate? Yes.
Data coming in, we've been well. Are you optimistic? Do you think that will take the line? Or how?
Last time I gave a colloquium, Oleg said in 10 years, we would definitely have it. Is that still the case?
I remember that being placed in 2007. They said we're going to have the HERA in 5 years.
Okay, well, we still don't have it. So, yeah, we're waiting for more data, but systematics are always there, and you need a way to go with them as well. But more data, then we get what we want.
I have a question from you online, but maybe you should read it out.
Oh, I hope it's not a deep question. X-ray luminosity parameter. Is this X-ray luminosity parameter? Oh, right. The X-ray luminosity parameter. Is this the X-ray luminosity of a certain patch of sky or sources? Sorry, I'm not a cosmologist. Oh,
No,
no cosmologist. Okay. I mean, so the X-ray is not for a particular. It's for a group of sources. Now, So we don't look at individual galaxies because then the simulation gets incredibly large and no computer can run that. So we look at much larger scales, like a collection of galaxies. So when we say the X-ray luminosity function, it's a collection of X-ray binaries that then produce this X-ray radiation, which then heats up the IGM. So that's what that parameter is. So it's a very technical question, but okay. I hope I'm not opening this up for many technical questions. Yes.
No, it's really,
Yeah.
that's done cosmology in a long, long time, but
All right.
in terms of the whole tension that you're saying, you know, in the local universe, we're getting this value for this parameter, in the very distant universe, we're getting a different value.
Yeah.
Are there any models that people are looking at that allow for a change in the Hubble parameter with age of the universe?
With like the age of the universe.
Or
So
every model that people looked at and said that has to be a fixed value
That is
throughout the
fixed,
entire universe.
the Hubble parameter itself is allowed to change with time. So
The
you can,
H0.
yeah, but the H0, yeah, then they produce different values regardless. But what I have seen though, there are some talks where people try to, so inherently dark matter and dark energy don't do anything. All they do is one pushes everything away, it doesn't interact, it doesn't do anything. And then the other one makes galaxies rotate nicely, but it doesn't do anything. And there are models where the cosmological models where dark energy decays into dark matter and all that kind of stuff, seemingly viable. They seem to solve this problem, but how? Oh, they seem to solve that problem in that narrow. That's the thing with cosmological models. If you have a best model, it needs to describe all the other data set. The reason why we say the lambda CDM model is the best is because mostly it explains everything. The non-standard models, they fail. They solve
They
one
really
problem
well,
and then they fail. Yeah. So yeah, definitely people have tried that kind of stuff. Yes, go ahead, so.
So I've never done cosmology before. I need to ask, how many of these cosmological models exist, and are they strictly from theoretical cosmology, and how much do they deviate from each other? Is there like a model that's far off from like how the Big Bang formed everything, or
Yeah. So how spread out the models are?
yeah.
Very spread out. So like I alluded to now, there are models where dark matter is interacting, you know, it's not non-standard kind of stuff. And they perfectly explain portions of, you know, of the data set. Even with EOR, there are kind of a range of models. Some with charged dark matter particles that steal energy from the surrounding. But what I can say is about cosmologists, we never have to worry about the mechanism. We can just say it fits into this parameter, and then we'll let the physicists, the guys with the theoretical work, worry about how can that, you know, be done in a way. Of which I met some colleagues at VERTS that work in that, and it was very interesting. That was really, yeah.
How different are the galaxies back then with the galaxies now?
They're slightly different in the sense that, for instance, now most of the galaxies they contain these X-ray binaries that most of them contain population 2 stars now. That will show those the galaxies that form them. They might be different morphologically as well. The stars that you form might also be different, but we haven't seen any stars that are there. I'm getting into the details of
That's what.
yeah, and of which it's an entirely
So
okay.
is that because of the material that was available
Yeah,
back then?
back then. Yeah, it's very different from our in a sense, trying to figure stuff out. How stars form now is different how they were forming back then, and how black holes form now is slightly different. We also have the black hole problem, which let's not get in there.
All those models are still there.
Yeah.
So is there any like category in this social model have like matter dominated, like non-matter dominated. These models actually explains that maybe darkening is dominated or perfect. Is there any like this kind of grouping or?
Yeah. Certainly, yeah, that's the running aspect, that certain cosmological models explain, certain part, but then they fail on other ones. But what we're trying to get to now is a unique model, a unique set of models, maybe small sample of models that then, try and explain most of the observation. For instance, in the EOR models, most of them we can definitely exclude them because there are models that are perfectly viable. They produce our non-universe, but they don't heat up the intergalactic medium at all. But with our data, we're able to show that no, those models are not viable, even though they produce the EOR period perfectly, but they fail at high redshifts. And so we can definitely say, we're cutting those out. So that's the essence. This. No questions. Good.
Can I ask one? Sorry, I can't even spell cosmology, but from an outsider's point of view, we talked about models, multiple models, and I think some of the ones that you showed, you get a huge number of parameters and variables. To what extent is the intercorrelation between variables within a model? How does that affect the performance of that model? So, would you get like a mathematical behavior rather than physical behavior?
So what we try to do is whenever we have a mathematical, for example, cosmological model, I'll make an example of the ER models. So they're motivated by the mechanisms that we see in our local galaxies. So they're not completely pulled out of, I don't know, anywhere. So they are physically motivated. And when we constrain the parameters, we get to learn what we know what those parameters mean, and we can link them to physical processes. I think is that your question? And I think the question is two parts. The second one is we have a lot of models. A lot of parameters. Yeah, in essence, we have a lot of parameters, but we never use any one data in isolation as well. And so, for instance, this only has 9 parameters, the model that I was showing you right now. But we have a lot of data to constrain those parameters. So we do sanity checks to check that we're not trying to, what is it called, overfit? Yeah, yeah, definitely. That we have a lot of data, fewer parameters. With any model, I think any physically motivated model, that's the standard. You can't overfit, otherwise you're overcomplicating the model unnecessarily. Okay, so
All right, I think let's stop it here and thank Dr. Charles.
okay, all right. Thank you everyone for coming. See you all in the next one. Hopefully not me, someone else.